My name is Talia, and I'm an incoming high school senior who's super passionate about teaching others math and chemistry. This YouTube channel helps students and is a supplemental resource to those who may be having difficulty in their chemistry classes. Today I'm going to be talking about basic quantum mechanics. If you need help with quantum mechanics, feel free to continue watching. And without further ado, let's get started. Okay, so in a previous video, we talked about how Bohr diagrams illustrate where electrons are outside of the nucleus. They can be in an infinite number of orbitals, but they always start by filling the first orbital. So quantum mechanics basically represents the 3D probability of where electrons can be located. And each element has four different quantum numbers. First is the principal quantum number, and that represents how close the orbital of the valence electrons are to the nucleus. So if n equals 1, the valence electrons are one shell away from the nucleus. If n equals 2, two shells away, and so on and so forth. Then there is the angular momentum quantum number, and that is represented by L. That gives the shape of the orbital. And L can be anything from 0, 1, 2, 3, anything up to the n, which is the principal quantum number, minus 1. So, for example, if in the second energy level, n equals 2, the angular momentum quantum number can be 0 or 1. And if L equals 0, that represents an s orbital. If L equals 1, that represents a p orbital. If L equals 2, that represents a d orbital. And if L equals 3, that represents an f orbital. So in the second energy level, an element would only have one s orbital and three p orbitals. There would be no d or f orbitals. Then there is the magnetic quantum number m sub L, and that gives the orientation of the orbital. So as you can see in this photo, the s orbital has 1 orientation, the p orbital has 3, the d has 5, and f has 7. So each orientation represents the different possible locations of the electrons in that orbital. M sub L can be anything from negative L to L. So using our same example, in the second energy level, M sub L can be anything from negative 1 to 1. And that is three numbers, negative 1, 0, and 1. And that will correspond to the orientation. And here is a diagram that basically shows each orbital and the number of orientations it has. When you put the orbitals together, they equal the electrons that would fill them, equal the amount of electrons that would be in a shell in a Bohr diagram. For instance, in the 2 orbital, we have 2s and 2p. 2s, the s orbital has 1 orientation, which 2 electrons will fit in, and the p orbital has 3 orientations, which will fit 6 electrons. And together, that equals 8, which is what the second orbital can hold, 8 electrons. And then we have spin quantum number, and that is represented as m sub s, and that gives the spin of an electron. So each orbital can have 2 electrons of opposite spin, and a positive spin is represented by an upwards arrow, and a negative spin is represented by a downwards arrow. So now we are going to take this information that represents the 3D probability of where electrons can be located in an orbital, and we are going to learn how to notate it. So again, we have principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. So first we are going to learn about orbital notation. And this is a way to express where the electrons are in the 3D orbitals. And orbital notation is based on 3 principles. We have the Aufbau principle, which says that the electron will occupy the lowest energy orbital available. Then we have the Pauli exclusion principle, which says how no 2 electrons in an atom can have the same quantum number. Thirdly, we have Hund's principle, which says how each orbital is occupied by an electron having 1 spin, and then they are paired with an electron of a different spin, which basically means that, let's say you have a p orbital. This is not how you would fill it, but instead you would first do all the positive spins and then all the negative spins. So this is the order in the periodic table of how the shells are filled. So we go from 1s to 2s to 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on and so forth. So we're going to try an example of orbital notation, starting with the orbital notation of oxygen. You're going to want to get your periodic table out. So I'm going to start by drawing the 1s orbital, which will have 2 electrons. This is my shorthand for arrows. You can write your arrows like this if you want. This is just quicker for me. And we know that the principal quantum number of oxygen is going to be 2 because it is in the second row, which means it will have 2 orbitals. We can also calculate the angular momentum quantum number, which will tell us the different kinds of orbitals we are going to have. So if n is 2, the angular momentum quantum number can be 0 or 1, which means there will be s orbitals and p orbitals. Next comes the 2s orbital, which has 2 electrons, and then we have the 2p orbital. And oxygen only has 4 electrons in the 2p orbital. So if we add all these together, this is 8 electrons, which is the same amount of electrons as oxygen. Next, let's do titanium. So you're going to want to locate titanium on your periodic table, and we're just going to go about the same way. I'm going to start with the 1s orbital, and then do the 2s. Then we have 2p, then 3s, then 3p, then we have 4s, and we then have 3d because the d block is 1 less than the s block in terms of the principal quantum number. So I'm going to write that down here. And there are only 2 electrons in that orbital. Okay, now we're going to continue with electron configuration notation. So electron configuration notation is the same as orbital notation, but you write out the orbital number, like 1s, instead of drawing lines for each orientation. And you include the number of electrons as a superscript. So as an example, 1s2, like that. And the periodic table shows the organization that you would use to write electron configuration notation. So if you look at my drawing, we have the S block, the D block, P block, and F block. So the S and P block are the same as the row number, like 1s, 2s, 3s, 4s. The D block is 1 less than the row number. So as you can see, the row with titanium in it would be 3D, 4D, underneath 5D, then 6D, even though 6D is in the 7th row. And the F block is 2 less than the row number. But as you can see, the F block fits into right here. So the 6th row, the 4F block would be in the 6th row if it was actually in the main chunk of the table. Okay, so now we're going to practice with electron configuration notation. Let's write the electron configuration notation for barium. So we will start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember the D block is 1 less than the row number, 3d10. Then we have 4p6 because it's in the P block. Also, helium is 1s2, so it's in the S block. So after 4p6, we have 5s2, then 4d10, 5p6, and then we have 6s2. That is the electron configuration notation for barium. So it's the same as the orbital notation, except I didn't draw the s orbital like this and do arrows. I just wrote 1s with a superscript of how many electrons are in that orbital. And as you can see, in the first shell, there are 2 electrons. In the second, there are 8 because the 2s and the 2p orbital. Okay, now let's do cadmium. Okay, so locate cadmium on the periodic table, and we're going to get started. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, um, 4p6, 5s2, then we have 4d10. And if you add all these electrons up together, we have 2, 4, 10, 18, 20, 30, 6. We have 48 electrons, which is the same amount of electrons in cadmium. So now we're going to talk about excited states and exceptions to electron configuration notation. When an atom is excited, one or more of the electrons can move up to a higher energy level. And this then changes the electron configuration notation to be different than what you would normally expect. So any combination can occur when an atom is excited, as long as the same orbital rules are followed. So for example, we have carbon. Normally, the ground state has an electron configuration of 1s2, 2s2, 2p2. However, in an excited state, the second electron from the 2p orbital can jump to 3s, and we can have 1s2, 2s2, 2p1, 3s1. As you can see, the 2p electron, the second one, moved up to the 3s orbital, and that is allowed because it's following orbital rules. And then there are also exceptions to the filling of orbitals, and these are normally transition metals. So examples include chromium and copper. So for instance, with chromium, it is expected that the electron configuration notation would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. However, actually, the one electron from the 4s orbital moves up to the 3d orbital to get 4s1, 3d5. With copper, a similar thing happens. As you can see, one electron from the 4s orbital moves up to 3d, and we have 4s1, 3d10. This is not the case with all transition metals. Another form of notation for quantum mechanics is noble gas notation. And this is a simplified form of electron configuration notation where you basically write the preceding noble gas and then the electron configuration that follows. So, for example, we have oxygen, which has an electron configuration of 1s2, 2s2, 2p4. The noble gas before oxygen, as you can see on your periodic table, is helium. So if we wanted to write the noble gas notation for oxygen, we would write helium in brackets and then write 2s2, 2p4 afterwards, because helium was a substitute for 1s2 since the electron configuration for helium is 1s2. And this isn't as helpful for elements with less electrons. However, when you have a large element that you want to write the electron configuration notation for, it like cesium, for instance, it's much easier to just write the preceding noble gas and then follow with the electron configuration. And again, you write the preceding noble gas as a substitute, and it's a substitute for the portion of the electron configuration that is equal to that noble gas. We can also write noble gas notation for ions. However, we know that ions are atoms that have gained or lost electrons in order to fill their octet rule. And we also know that noble gases have 8 electrons in their valence shell. So when an atom becomes an ion, it will have the electron configuration of the following noble gas. So, as an example, nitrogen, the atom, has an electron configuration of 1s2, 2s2, 2p3. It gains 3 electrons to become this electron configuration, but 2p6 it is the end of the electron configuration for neon, because neon is the following noble gas, and that has 8 electrons in its valence shell, which is what an ion aims to have. So as I wrote here, it gains 3 electrons to have the same amount of electrons as neon. They are both now stable and have 8 electrons in their valence shell. So nitrogen becoming an ion and writing the electron configuration notation for that does not mean that the element itself has changed. It is still nitrogen. There are still 7 protons, and you know that an ion gains or loses electrons, which is expressed in the electron configuration notation, but that is the same amount of electrons as the noble gas neon. And if you wanted to write the noble gas notation, you could just write neon because now the amount of electrons are the same. So this can tell you that by fulfilling its octet rule, an ion is really just the atom with the same amount of electrons as the closest noble gas, because noble gases have full valence shells. Okay, so now we're going to practice writing noble gas notation for these atoms. So you have zirconium, francium, astatine minus, and selenium 2 minus. Remember that these are both ions, so your noble gas notation will change. So try these on your own, and then I'm going to show you the solutions. Okay, so with zirconium, we are going to first look at the preceding noble gas, which if you look at your periodic table, the preceding noble gas is krypton, number 36. So I'm going to write Kr in brackets, and then write the rest of the electron configuration, 5s2, 4d2. With francium, the preceding noble gas is randon, so I'm going to write randon in brackets and then 7s1. That's the rest of the electron configuration. And remember that randon substitutes all of the electron configuration of francium up to randon. Astatine minus, it gains 1 electron, so it will then have 86 electrons, which is the same amount of electrons as randon. So we can just write the noble gas notation as Rn in brackets. And the same thing goes with selenium. It gains 2 electrons to have the same amount of electrons as krypton. So you can just write krypton in brackets. And that concludes our discussion on basic quantum mechanics. I hope you enjoyed this video on quantum mechanics and that you were able to broaden your knowledge of the subject. Next week, I am going to be diving into a new unit, and we are going to be talking about chemical families, as well as atomic and ionic radius, which is the introduction of our discussion about periodic trends. So if you need clarification on those topics, feel free to join me back next week. I'm also going to be putting a link in the description of both my website, where you can schedule tutoring if you would like, as well as a video by Professor Dave Explains, which explains quantum mechanics really well, in my opinion. I feel like if you still need help, he would be a wonderful resource. So if you need that, you are welcome to check it out. Again, I hope you enjoyed, and good luck with learning your chemistry.